All right, we're still working with sequences, but there's a little bit of notation that we need before we go on, and that is this idea of factorial notation. And this pops up when we see products of successive integers. And so rather than, writing it out all the time and, getting a cramp in our hands, we like to have a piece of concise notation for this. And all the factorial notation means is that when we see an exclamation mark following a number, and that we read that as n factorial, not n really loud, which is what teachers like to say sometimes. It just means that we take the product of the value that we see and everything lower than it up until 1. Okay, so and by definition we take 0 factorial as 1. Okay, that's just a given. Okay, when we go through these and just kind of see what the numbers would be, 1 factorial would be, well, it would just be 1 factorial. 1 factorial would be 1 times, and then I have to stop at 1, so it's just going to be 1. 2 would be 2 times 1, or 2. 3 factorial, now this is where we have to start to be careful, would be 3 times 2 times 1, which is 6. 4 factorial would be 4 times 3 times 2 times 1, okay? And when we do that, it's 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120, okay? And 6 factorial is effectively going to be 6 times 5 factorial. This is another way you can write this whole thing. And so then we just have to take our result from 5 factorial, which is 120, multiplied by 6, we get 720. Okay, so the reason I had us do these is that these values of 2 factorial, 3 factorial, 4 factorial, and 5 factorial, and 6 factorial happen to pop up quite often. So it would be useful to kind of associate this 3 factorial to 6, 4 factorial to 24, rather than repeatedly use the definition. You certainly can use the definition and it'll always work, but if you can commit those to memory, that would be great. Okay, so now let's get some practice evaluating expressions containing these. Okay, so all right, so we can certainly do the number crunching, and hey, if you want to, go for it. Okay, what I'm going to do is I'm going to be clever. And I'm going to say that 9 factorial is 9 times 8 times 7 times 6 times 5 times 4. And you don't have to write this out. I'm just doing this to prove a point. And then the denominator is 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so put a different way. And then I also have 2 times 1. Okay, put a different way. This is 9 times 8 times 7 factorial, right? Because 7, 6, 5, 4, 3, 2, 1 is all multiplied together in both the numerator and denominator. And so I have 7 factorial numerator, denominator. Those can cancel, and I'm just left with 9 times 8 over 2 times 1. Okay, and I can certainly reduce here. That's a 4, and I get 36. Huh. That was easy. Again, if you want to number crunch, your calculators, I believe, do have a factorial symbol under, for many calculators, it's under the PRB menu for probability. So you might just have to locate that. Or, hey, you know what? You have this thing called Google, and you can Google your calculator model and factorial, and it'll come up with a guide on how to get that. All right, next, we can think about this, we look at it and we want to cry a little bit, but at the end of the day, we just think a little bit carefully. Okay, so this is going to be n minus 1 times n minus 2 times n minus 3, and so on and so forth, down to 3 times 2 times 1. And the denominator is going to be n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Notice that these are the same up until n. So those I can reduce, right? They would cancel out because they're all multiplied, and I just have 1 over n. Okay. Another way that I see this is that the denominator I'd write as n times n minus 1 factorial, and then n minus 1 factorial in the numerator, and those would cancel. So that's another way of writing it. this last example for now is just going to require us to kind of use the same idea from this last example and recognize that 2n plus 1 is 2n plus 1 factorial is 2n plus 1 times 2n times 2n minus 1 factorial, and then 2n minus, so that'd be 2n minus 1 times 2n minus 2 times 2n minus 3, da 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 da, and the denominator already has that 2n minus 1 factorial, so I could reduce those and say that the numerator is just going to be 2n plus 1 times 2n, and I could distribute that out if I wish, but that's all I need. Okay, so get some practice working with factorials, get those numbers kind of committed to memory, and kind of have fun. I like working with factorials. But then now the idea is we're learning all this in the context of sequences. So let's get some practice with it in sequences. Okay, first 4 terms. So I'm gonna, if it's easier for you to do like an n and a cn table, that is totally okay. Just like you would do an x and y table, that's fine. So 2, 3, 4, okay. So then for 1 it would be 2 to the first, which is 2 over, and maybe let's just simplify this as 2 to the first over, and then this would be 2 factorial. So this is just going to be 2 over 2, which is 1. Okay. For 2, I would say that this is going to be 2 to the 2 over 3 factorial. So this is 4 over 6, which I can simplify to 2/3. Next, 2 to the 3rd over 4 factorial, 3 plus 1. Okay, so this is 8 over 20, which I can reduce as 2/5. Okay, and for 4, 2 to the 4th over 5 factorial, so this is going to be 16 over 120, and I'm sure I can reduce that by 4 at least, so it'd be 4 over 30, and I can go even a step further, so 2 over 15. Okay, so note that when we see it in sequences, it's not going to be terribly different than what we've seen before. We just might have to evaluate it and go from there.